If you travel close to the speed of light, so if you had a spacecraft traveling close to the speed of light, then distances shrink from your perspective. The one number I always have in my mind is at the Large Hadron Collider at CERN, the protons go around the ring, which is 27 kilometers in circumference, and they go around at 99.999999% the speed of light. So close to the speed of light. At that speed, distances shrink by a factor of 7,000. And so that ring is something like 4 meters in diameter to the protons. According to the laws of physics, if you can build a spacecraft that goes very close to the speed of light, you can shrink the distance to the Andromeda Galaxy, and therefore the time it takes to get there. You could traverse across that distance in principle in a minute, according to physics. However, if you came back to the Earth at that speed to tell everybody what you'd found, at least 4 million years would have passed on the Earth. We could, in principle, explore the galaxy and beyond, but getting to chat to everybody about what you found is forbidden by the structure of the universe. That's the way that relativity works.
Is time travel possible? It's kind of obvious to say it's possible into the future, because of course that's what we're doing. We're moving into the future. It then gets interesting because you say, well, why do we have to go into the future? Why can't I stop going into the future? Well, you can vary the rate at which you go into the future relative to someone else. For example, if I was to get in a rocket now, and let's say go to the Andromeda Galaxy, which is 2 million light years away, and then turn around and come back again. If I go close enough to the speed of light, I could arrange it. So I would age, let's say, a year on the outward journey and a year on the inward journey. But 4 million years would have passed on Earth. So I would come back on that journey 2 years older, but I'd arrive at the Earth 4 million years in the future. So that's special relativity. That's Einstein's theory published in 1905, not even the theory of gravity. So time travel is possible into the future, and you can vary the rate you go into the future relative to someone else by the way that you travel around. Will we ever travel at the speed of light? No. So that's a simple answer. Anything that has mass cannot travel at the speed of light. But anything that is massless, has no mass, has to travel at the speed of light. So photons, which are particles of light, for which, by the way, Einstein got the Nobel Prize, essentially. There's something called the photoelectric effect back in 1905. So Einstein didn't get the Nobel Prize for relativity. He got it for this idea that you can think of light as a stream of particles hitting something and firing electrons out of it. So it's called the photoelectric effect. The way we understand physics at present, photons travel at the speed of light, not because they're light, but because they have no mass. So it should really be called the speed of massless particles. So will we ever travel at the speed of light? No, unless you have no mass, in which case you have to.
It's one of the oldest questions in mathematics. It's got a name, actually, called the honeycomb conjecture. Mathematicians have worked on it for thousands and thousands of years, and it's only recently that the honeycomb conjecture was proved. Here's one of the proofs. A huge paper, pages and pages, complex mathematics. And it turns out that hexagon is the most efficient shape. The bees knew what human mathematicians didn't know for thousands of years. Actually, I'm using know in quite a loose sense there. There's still a great deal of debate amongst biologists as to how the bees actually do it. But what is agreed upon by the mathematicians and the bees is the hexagon is the most efficient shape. That just shows you it's a beautiful thing. Mathematics is the universal language.
What would happen if Earth or a human fell into a black hole? It depends on the mass of the black hole, is the technical answer. So if it's a small black hole, by which I mean just, a few times the mass of our sun, you get ripped apart by the tidal gravitational forces before you actually fell in. But for the very big black holes, the one we have a photograph of in the center of a galaxy called M87, which is a very big one, it's something like 6 billion times the mass of the sun. So a supermassive black hole in M87. And if you fell towards that one, then, as far as we know, you would fall across the horizon into the interior of the black hole, and you'd be unaffected. You wouldn't notice as you fell across the horizon until you approach the singularity. So you go to this singularity, which is, in Einstein's theory, the end of time. And just before you get there, you get spaghettified, which means you get stretched in one direction and squashed in the other, and even your atoms get ripped apart, and then you go to the end of time.
Saying that all the particles in the universe need to be held together by something, and this is the glue, if you will, that's holding everything together.
In a way, it's that you get mass. So these particles are solid because they're interacting with this stuff, except for light, which travels at the speed of light because it doesn't interact with
I'm fascinated by people that think on this level. For someone to conceptualize this and then set out to prove that it exists and then prove that it exists.
Well, this is the beautiful thing. So this is a prediction from the 1960s, a mathematical prediction. Then, about 10 years ago, we decided to build the biggest scientific experiment ever built, 16 miles in circumference underneath Geneva. We accelerate protons to 99.999999% the speed of light, at which speed they circumnavigate this ring 11,000 times
a second. You get them spinning around this ring really fast.
One the other way. We collide together 600 million of these every second. In every collision, we create the conditions that were present less than a billion per second after the Big Bang. We take photographs of those 600 million collisions per second, and we find out this guy from 1965 was right.
It is impossible to visualize the scale of the universe. In the piece of the universe we can see, there are something like, roughly, 2 trillion galaxies. We haven't counted them all, but that's an estimate based on surveys of the local universe. 2 trillion, 2,000 billion galaxies. And each galaxy is, let's say, around the size of the Milky Way. Some are bigger, some are smaller, but the Milky Way has 400 billion stars in it. It takes light over 100,000 years to cross a galaxy, and there are 2 trillion of them in the piece of the universe we can see. And we're very sure that that piece that we can see is a small bit of what may be an infinite universe beyond. We don't know, actually. And I always say, don't get worried about that, because nobody can picture it.
We now know that the answer to the question, why is life on Earth so varied, is actually the answer to the question, why is the DNA molecule itself so varied? What are the natural processes that cause the structure of DNA to change? Well, part of the answer, actually, doesn't lie on Earth at all. It lies up there amongst the stars. And I'll show you what I mean using this, which is a cloud chamber, a piece of apparatus that has a unique place in the history of physics. Now look at that. You see that cloud, that vapor trail? That's a cosmic ray. That was initiated by a particle, probably a proton, that hit the Earth's atmosphere. It almost certainly originated outside our solar system and was accelerated by the magnetic fields of our galaxy. It may even have begun its life beyond our galaxy. Imagine if one of those hits the DNA of a living thing. What that will do is cause a mutation. That mutation may be detrimental, or very, very occasionally, it might be beneficial. Maybe one of the key mutations that was selected for over the millennia that led to some trait in me was caused by some particle that began its life, perhaps in a massive supernova explosion.
Anything that has mass cannot travel at the speed of light, but anything that is massless, has no mass, has to travel at the speed of light. So photons, which are particles of light, photons travel at the speed of light, not because they're light, but because they have no mass. So it should really be called the speed of massless particles. And that's built into Einstein's theory. It was subsequently realized, basically.
The majority of our galaxy is made up of something called dark matter. That's a mysterious substance. We don't yet know what it is. We strongly suspect it's some kind of subatomic particle. So things like the electrons that go around the nucleus of an atom, but with different properties that interact very, very weakly indeed with the material in the stars and planets, and indeed with the material that makes up you and me. I don't want to give you numbers because this is the cutting edge of physics. These things are changing all the time. But I'll give you a rough estimate. Something like 5% of the mass of our galaxy is made up of the stars that we see shining in the sky. Around 10% is made up of dust and gas. And something like 85%, perhaps more, of the mass of our galaxy is made up of dark matter. And we don't yet know what that is.